Good afternoon, everyone. Welcome to this afternoon's Olympus Inspection 360 webinar. I'm so glad that you've all joined us. I've been really excited about the webinar that we're going to have today with our guest speakers on a very important topic. And so I'm glad you've joined us. Look forward to the research we're going to hear about and also the conversation that will follow afterwards. I'm Michael Hall. I'm one of the X-ray specialists at Olympus. And my role today is basically just moderator or MC, and I don't want to take much airtime away from Professor Richter and Ms. Cagliari, who's the student researcher. So with that, let's jump right in today's topic about urban soils and human impacts. And this concept of human impacts is a bit of two directions. What is the impact of humans upon the soil, and what's the impact of the soil upon humans? And in particular, we're looking at lead contamination in communities. So thank you for joining today, and we've got a world-renowned expert to help lead us through this discussion. I did just want to mention who we are as Olympus. Some of you may be familiar with Olympus for their digital cameras, or in past their film-based cameras. This is the same Olympus organization. Also make microscopes, and we're a global medical technology company with a lot of endoscopy and therapeutic solutions. But we also have industrial technology as well, which is what the X-ray technology we'll be talking about today. But the purpose of Olympus, our company's purpose, is to make lives healthier, safer, and more fulfilling. And so whether it's more fulfilling by capturing that family photo, or healthier through endoscopy and therapeutics, or safer through our industrial technologies, the inspections that we provide, this is the mission that unifies the technology that Olympus develops. And I think if you think about these concepts of safe, healthy, and fulfilling, there's a lot of things that can be put in the center of this, the overlap of this. But I think the concept of urban soils definitely fits in there. We want soils to be safe. We want the soil to be healthy for itself and healthy for our communities, so that whether we are gardening or playing on the playground, we can have a safe and fulfilling life. And so this is part of the connection to our topic today, to Olympus's mission. We will be talking about several topics connected to lead in soils, but one of the technologies involved in this will be X-ray fluorescence. I know many of you on this presentation today may not be familiar with X-ray fluorescence at all, so I'll just give a quick tutorial in terms of how this works. This is a handheld instrument, portable. Many people compare it to like a radar gun that law enforcement might use, so similar format there. It is X-ray based, so X-rays come out from the instrument and go into the sample, into the soil sample, rock sample, whatever sample you might be analyzing. Those X-rays go out from the instrument into the sample. The sample then absorbs those X-rays, and the sample becomes energized. The iron in that sample, the chromium in that sample, the nickel in that sample become energized. It's similar to, sort of giving a sugary drink to a toddler. The elements become quite energized there. And what they do is then in return give off their own X-rays. But the X-rays that come back are different than the X-rays that went out. So the X-rays of iron look different than the X-rays of chromium, which look different than the X-rays of nickel, of lead, of mercury. And so these X-rays are a fingerprint of the material's composition. From there, the technology works similar to your digital camera. There's a detector, there's a microprocessor that converts these photons or X-rays into a digital signal, and does a lot of fancy math in the background to ultimately give you material chemistry, how much arsenic or cadmium or chromium or lead is in this sample, how much iron or quartz or aluminum might be in this sample. And all of this happens basically at the speed of light. We're talking about 2 to 3 seconds, 20 seconds maybe max. So quite fast, completely non-destructive, safe, handheld, portable. And this technology undergirds part of the research that Professor Richter and Ms. Cagliari will be talking about in their presentation today. So I do want to introduce Professor Richter, and I'm very grateful for him to commit his time today to this presentation. He's a professor of soils and forest ecology in the Nicholas School of Environment at Duke University, and he holds dual appointment in the Earth and Climate Science Department, as well as the Environmental Science and Policy Department. And I think this dual appointment reflects his long-standing commitment to thinking not just about the hard science of soils and ecology and forest science, but also thinking about how do we take that science and translate it into policy and practices that help our environment and our community. And so he stands at the intersection of both of those things. He's been directing the Calhoun soil ecosystem experiment for many years. This is a 60-year outdoor experiment that's been going on, and he's been associated with this for almost half of the Calhoun soil ecosystems experiment there. Formerly was at Oak Ridge National Lab, and I'm certainly not a soil scientist, but as I read up on Professor Richter's research, one of the concepts that popped out is this idea of Anthropocene soil. I don't know if you coined this term yourself, Professor Richter, but I know it's central to your research. The idea that the soil is living within the human epic, that the human have impacted the soil, and the soil have impacted humans, and we live in synergy with one another. And I think that's certainly central to our concepts today. If you want to get to know Professor Richter more and his research, if you Google either of these here, Implications for Soil Health from the Soil Health Institute, or a nice interview he did with British Soil Science, this is a good general introduction to Professor Richter. These slides will be available afterwards, and we can share those links with you as well. He'll be joined today by Miss Julia Cagliari. I've had the privilege of knowing Julia for actually a couple years now. She's one of these high-achieving individuals that makes you feel like you haven't done enough with your life, but she's already made quite an impact on science. She's a double major in mechanical engineering and environmental science at Duke University, and is a two-time national and international science fair winner, all before going to college. So give you a sense for Julia's work ethic and ambition in the STEM sciences. And if you want to find out more about Julia, you can follow a couple of these links or Google them. She's already had 2 published publications prior to starting her research with Professor Richter. So without further ado, I want to turn it over to Professor Richter and Ms. Cagliari for today's presentation. Well, I'll be back on at the end to take questions. Feel free to put any comments or questions you have in the attendee chat as we go along.
So thank you, Michael, very much for this opportunity, and actually for the opportunity of working with Julia, because it was only you and your colleagues that put the 2 of us together. Julia is only a first-year student at Duke, and oh my gosh. So wonderful to work with somebody who comes in as a first-year student with experience with XRF. So she in short order has made impact on our work. Welcome everyone, and Julia, would you like to say, I don't know, formally a hello?
Hi, Michael. Thank you for having us. I'm super excited about this, and Dr. Richter and I and the rest of the lab team have done a lot of really cool work, so I'm excited to share that today.
Yeah, great to see you, Julia. And so in the university, the wonderful thing about being able to do research is the wonderful students that keep coming. And Julia is just, she doesn't know it, but she's one in a long parade of absolutely wonderful students that come through Duke and come through the university systems. And 2 other students, or 3 other students here I have listed. Anna Wade was a recent PhD graduate, and she and I began this soil lead work with our XRF in Durham. and is now employed by the EPA. Eni Bareri is a master's student whose work Julia and Rhett Grewal and I are helping move along. And we'll talk a little bit about our early data from Eni's work. But for the most part, this comes from an environmental science and technology published paper. It's an open access paper. And if you were to Google just, I don't know, Wade, Richter, Durham, lead, you would find the paper in short order. So if you're really interested in what we're doing here, our slogan, our lab has a slogan. It's every city needs a soil lead map. And we're not literal there, but we are very earnest about that slogan. Every city needs a soil lead map, because what's happened to our little project within Durham is it's led me to all of the city agencies that have anything to do with the environment or with waste or even the fire department, because there's high level concentrations of lead in much of the paint that's on our fire hydrants. And in any event, it's, you know, every city needs a soil lead map. It's a bit facetious, but on the other hand, it's just having a little project like this becomes not just research, it becomes an environmental education project. So thank you, Olympus, I guess you could say, for opening this opportunity to the scientific world, because, for example, I'm a wet chemist. I'm a wet lab chemist. And I've been so thrilled to have this XRF that increases the speed at which soil samples move through my lab by at least 100 times. And the concentrations range over 5 orders of magnitude. It's really spectacular what technology is allowing my generation of scientists to do. And then just to think about Julia's generation, I mean, it's really spectacular. Science doesn't give us all the answers, but it certainly gives us a lot of tools and a lot of insight. So just to conclude this first slide of Durham, North Carolina, the Bull City, you know, it's a project in which we've made visible the invisible. Legacy lead is out there in city environments, and this particularly this instrument gives us the ability to be confident, either using it in portable mode or back in the lab, which we greatly prefer. You know, we're making visible some problems that have been forgotten, basically, have not been looked at. Now, I remember exactly the pair of maps that startled me, that made me think I can do something here. Particularly with my students, this is a very fascinating topic, and this is a map made by Howard Milkey. He's 85 years old. He has more energy. He has as much energy as Julia, I'll tell you that. He's 85. He has worked in Tulane University's medical school, mapping city soils of their legacy metal concentrations, and here is his hometown in New Orleans, and you can see the soil lead map and the various concentrations in the legend at the bottom right. You can see the old quarter of New Orleans is just the hot spot for lead now in these different neighborhoods. Now, he's repeated this analysis since about 1990, but the startling comparison was with children's blood lead in these same neighborhoods. And I'm going to show you the blood lead map, which is basically the same map as the soil. Here's the blood lead map. I dare you to kind of look at those two maps and say there's much difference. And so Howard's been on a 35, 40-year career. He's finally retiring. This is basically his life's work. And when I saw these two maps, I'm just startled, and to realize that my colleagues in the soil chemistry profession at large, hardly any of us work in the city. And yet here are the soils that are closest to us as human beings. And so more about this story and the correlation here as we move through this. A little bit more of the history of lead, at least in America. Lead, I've used the word legacy lead. It's because the circulation of lead in the contemporary cities of America today is much less than it ever has been. Decades are passing by, so that's the good news. And so you can see lead in fresh paint. That's about half of the lead that has been brought into the urban environment, and the other half comes from leaded gasoline. Lead was taken out of gasoline in America by the early 1980s and really represents a big pulse in the 1970s, though. About a quarter of all the lead that was added to our city environments was added in the 1970s in leaded gas. But the good news is we've got it out of these products. It's been out of the products for 40 plus years. But the problem, the bad news, is has to do with the chemistry of lead. It is very insoluble, highly insoluble, especially in the soil environment. And so it accumulates in the soil environment. And it tends not to dissolve and leach away like many other chemical elements might, but it really is held with high affinity for the soil clays, especially, and the soil organic matter. And so that's, there's a bit of good news and there's a bit of bad news. Well, the other part of this problem that makes it a very important environmental health problem, and it will continue to be such for decades to come, is our scientific understanding, our medical understanding of the toxicity of lead. Lead is known as a non-threshold toxin. There are many toxins in the environment that they have a certain threshold under which they really don't affect you, and then you go over that threshold, and then it becomes a concern to your mental state, or to your behavior, or to your physical prowess. But lead, we now believe that lead is one of those relatively few toxins where you don't want any of it in your environment. Yes, there's a limit to that in terms of practical livelihood, but we do want to identify where lead is in our city environments and do something about it. And we actually think we're entering a new stage in terms of remediation for lead, and it's a very exciting stage. And I'll try to reveal what I mean by that as we move ahead. And I might say one last thing about this point. It's all in red here. And so as we have removed lead from paint, from fresh paint anyway, and from gasoline, the medical science community, you can see, has reduced the blood lead concentrations level of concern, let's call it, from 60 of these units, micrograms of lead per deciliter of blood, from 60 down to 5. And now they say not only 5, that's just a target. That's not a safe level for blood lead level. And so CDC has recently had a working group recommend that 5 it be lowered to 3. And in any event, it's at the same time we've taken out lead from most products, not all, still in some water systems, some other forms of lead still are actively bringing lead into the human environment. But from the big two sources here, gasoline and paint, it's been out of circulation for a number of decades, and that really has had a huge effect on exposure. Another good news story is that exposures are way down compared to what they were during the 1970s in the urban environment, for example. But the underside, the complexity is that medical scientists are now more and more realizing that the concentrations, even at low levels, can be harmful to the human body. Now, our overarching hypothesis is that as these decades go by, city soil lead concentrations are decreasing. That's our hypothesis, and that's in response to the fact that soils are living, they get mixed, they erode away, and the high amounts of lead that were added by both fresh paint and aging paint and also gasoline are slowly dissipating. We don't know at what rate because we have no observations except for good old Howard Milkey, the recently retired medical doctor soil chemist, and his papers. He basically, that New Orleans data set in which he's repeatedly sampled the soil of soil in New Orleans can quantify the decreasing rate. Well, it's our overall hypothesis, and it's not really, remember, it's not really saying the problem is entirely going away, but it's definitely leading us into a new era of soil lead remediation in the city. All righty. If I was to teach a course in soil science, I might use this kind of diagram. And it's what we call the natural model of soil. And it's due to Roy Simonson's, it's a cartoon of soil processes creating soil in the natural environment. Well, in the city environment where my colleagues do not study, and I have only started to study soil in the city for 4 or 5 years, we need to modify this model and bring it into the city environment. This is a natural way of looking at the soil. And so my student Anna Wade did her best to take Simonson's process model and adapt it to soils of the city and also adapt it to the lead problem. And so we're, in a sense, we're using lead to tell us about how soils work in the city. And so, of course, on the left, we have what Simonson did was he said there are inputs into soil. And so here's a VW Bug from the 1970s. You know, it was really appalling the amount of lead that was being circulated in American cities. It was also in fresh paint and in aging paint. So here's the 2020s. The legacy lead from gasoline is now in the soil, insoluble, and the older homes of Durham and of other cities also are still, the exterior paint is still contributing some lead to the localized environment around the older homes. Of course, we have inputs from composting and yard fill. We have mixing of cut and fill and construction. We have translocations like trees tip up and mix the soil. We do have some leaching. It's not a very big process. Some urban areas have trees in city parks that cover the soil with leaves. That's a good thing. And then we have transformations, different kind of chemical reactions that either stabilize or make more bioavailable the legacy metals. Then we have outputs as well. And so over decades of time, erosion is moving lead off the land, off the city surfaces into local floodplains. But in any event, our hypothesis is that these processes are contributing to a slowly decreasing concentration of soil lead. And my colleagues and I want to resample 6 or 8 U.S. cities that have been sampled in the past, much like Howard Milkey's work, and expand that New Orleans work out to 6 or 8 American cities. That's our ambition, and maybe I'll be lucky enough to have a student like Julia work on that with me. All righty, let me show you something about our study, just a couple of slides about Durham. I was new at this, so I needed an environment where I could work with students and we could learn together. So we went over to the East Campus of Duke University, and we basically started at this intersection, point 0, and we collected a soil sample every 100 meters as we walked around the perimeter of East Campus. And we took 2 samples, one at the street side, right next to the street, half a meter away from the street. And then we walked, I think it was, it was about 10 to 15 meters inside the street, but we paired the samples. We had one that was street side and one 50 meters in the grassy areas of East Campus. And you can see the data over here. It's been 40 or 50 years. So there's been mixing and gardening, and the grounds crew at Duke has taken care of some of the street side soils. They brought in new soil, and so you have lower levels, and then you have other street side soils that are really rather high, 1,000 parts per million. We had one corner there at Broad and Markham, way up in the northeast. We've repeatedly sampled that. And that intersection has 3 old gas stations on 3 of the 4 corners, and we assume that that's from some kind of leak that went into that corner of northeast on East Campus. We've repeated those data, but that's 3,000 parts per million. That's 10 times what EPA says is a safe level. And in fact, most of us soil chemists think that EPA's level of safe lead at 400 ppms needs scrutiny and lowering. So that's a considerable amount of lead there that still exists 40 years after lead was taken out of gas. And so, yeah. So let me move on here. We can either, let's see, yeah, Kevin Tan, who is an undergrad, he said, let me take that data and let me make a 3-dimensional graph of it. And so here's what it is. Kevin and I worked at the southeast corner of East Campus, and we took our XRF for the first time. We took it to the field. Michael and his colleagues claim that it's portable, and it really is. And what we did was we walked around this Southeast Campus lawn. We know that it's been a lawn for 50, 60, 80 years, and we could still see the legacy lead right around the perimeter of that lawn, and we detected, hundreds of parts per million in some cases. But the internal part of that lawn is 50 parts per million or less. And when I read the literature about aerosol deposition of the lead particles, most of those lead particles, the literature tells us, were deposited quite quickly. Some of them went into the general atmosphere and moved long distances, of course. But most of that lead burden was deposited close to the streets. And that's what it appears here that was verified 40 years after lead was taken out of gas. Another thing we did was we decided to expand that, and I had more fun on this in this class. I held a class to do this work, and I took my 6 students and we walked 26 miles of Durham streets, collecting soil every 100 meters. Some of the streets are high traffic flow streets, and some of the streets are residential streets. And so here's a concentration map that we were able to generate. And we, statistically, the high flow streets like Roxborough and Club and West Main for that matter, even though it's been 40 years, those are the streets that still have the highest lead burden still in evidence. Lower traffic streets like Glendale here, they just didn't get the traffic flow. So that signature is still imprinted on the street side soil. And again, this is within a ½ meter of the curb. So it is really literally street side. Anna and I went out and we sampled houses across Durham, and the strongest covariate was house age. And we sampled 2 kinds of soils that were within 1 meter of the foundation, and then we took yard samples out across the front and side yards of I think it was 62 houses. So this is it's really a first estimate, but boy, it gave us the age, house age signal loudly and clearly. Here's the 400 parts per million EPA soil guidance concentration here on this graph. And you can see that a large majority of the older homes, older than 1950, have concentrations well above the 400 part per million level. And Anna has added this. There's a soil guidance level 2 that EPA is considering, and they're considering, reducing that concentration of soil lead to 100. That's more of an unofficial, but what an amazing graph that reveals. And I might say that this is the second city in North Carolina that has had a study like this. Well, to wrap up, what did we learn? We learned that street-side Durham soil still harbors legacy soil lead, especially along streets with high traffic flow. The average is pretty high, 150, and it's based on a pretty good sample size, 400. Soils adjacent to homes are also issues, have issues with lead, very high concentrations, averaging over 600 parts per million, and a pretty good sample size of 200. And of course, where kids, especially less than 5 years old, lack the defenses that even adults have to exclude lead from the bloodstream. Children, particularly the very young, younger than these kids, are even more susceptible. But kids even up to 5, it's really a tragedy in regard to how can you keep kids from playing in the dirt? That's a sad tale. But in any event, we hypothesize that while soil city lead may be decreasing over the decades, and again, it's a hypothesis, if this is the case, then hotspots surely remain, hotspots of lead. Lead is so insoluble. And so such high soil lead may be increasingly predictable, we think, in a hypothetical situation, with a hypothetical perspective. And they may represent a relatively small area of the city. So a question occurs to us, is soil lead becoming a more remediable problem? If it is, that represents a policy choice that becomes easier and easier to make, for sure. And so as we move along, I'm going to turn the mic over to Julia in a moment, but just taking a breath here for a second. Anna graduated in 2020. We continued to be interested in soil. This is a fascinating topic, and it's one that has so much potential because basically science hasn't been there in the city looking at soils in the ways that we've just talked about. There are exceptions, very important exceptions. Howard Milkie is one exception. New York City has a very active group of soil scientists. There are really brilliant exceptions. Baltimore is example, Indianapolis, but they're generally few and far between in comparison to where we all live. Every city needs a soil lead map, as I said before. Well, we got interested because of a master's student, Annie. It got me interested in pursuing a question of, well, where are these hot spots, Dan? She would say, where are these hot spots? And so we got interested in waste incineration, which was a very popular engineering practice for managing city waste and household waste for decades. And we learned that there were 4 parks in Durham that had been waste incinerators run by the city for on the order of 50 years. And so since in 1955 was the time where Durham closed these city-run waste incinerators. They were in different neighborhoods. And so they closed them by about 1950. And very happily, old newspaper articles pronounce that they were converted to playgrounds and to city parks eventually. Unfortunately, that's a date where there's not a lot of people that can tell you exactly what was going on, but old newspaper articles are readily queried in our library, and we have 3 great newspapers in Durham. They're all online, and so we were quickly typing in incinerator to see what we could learn, and we learned a lot in a hurry. So we learned that there were 2 generations of waste incineration in Durham, those pre-1955, that neighborhood incinerators, and we think that many medium-sized cities were like this. 50-foot stacks, so the smoke was definitely in the human environment, and these, in Durham anyway, they would burn about 5,000 tons per year. Well, you ask yourself, what about all those so-called ash elements, all those elements that do not volatilize, that become part of the ash, elements like lead, like other metals. In any event, we found in the newspapers a lot of neighborhood complaints about the nuisance of smoke, odor, rodents, dust. And the city was really pressured, ground up from neighborhoods up, to do something different than these neighborhood incineration procedures. And so they opened a centralized incinerator in '55, right outside of town. And it was state of the art. So the city was very excited. And so this is an ongoing project, and I'm going to turn this over to Julia and have her tell us about herself and a little bit about how she's worked in our lab.
Thank you. So I joined Dr. Richter's lab about 6 months ago at the beginning of this, kind of the start of this new project. But I've been working with the XRF for about 3.5 years now. And I'm super involved in the new project in Dr. Richter's lab. We're canvassing parks and taking samples, and we've really jumped into that. But my particular area of interest right now, at least, is kind of optimizing this process of using PXRF. So as Dr. Richter mentioned earlier, compared to wet chemistry, the XRF is at least 100 times faster. I'd venture to say that's maybe a conservative estimate. And with this, a lot of scientists using this today are creating a pucking method. So if you see the plastic cylinder on the left side, that would be a soil puck, and it's just a plastic piece covered in thin film and stuffed full of soil, which kind of densely compacts it. So traditionally, you would take a soil sample, dry it, grind it up to get a uniform, coarse particle, and then smash it into the sample cup and create yourself a puck. And these pucks are fine. They're easy to label. They're easy to reuse, so you can do a lot of repeat scanning, which is nice, but they take absolutely forever to construct. Less time than wet chemistry, but significantly more time than just kind of dumping the content of the dirt onto the face of the Olympus Phantom device. And the screen there is covered in a thin film to protect the instrument, but we've started just kind of pouring our ground and dried soil samples directly on the face of the machine, using the lead cap to cover it and just running our tests that way. And we've saved ourselves hours and hours without pucking. And we were pretty sure that this was a solid approach, a solid method. We were getting good results, but we decided to create a little experiment just to make sure that the time we were saving wasn't compromising our results. So what you see here is a graph comparing the results of using a puck or just pouring directly onto the instrument stage. We have an R-squared value. I think we did about 32 samples, and an R-squared value super close to 1. So we were really able to optimize this process and move through a significant number of samples much, much faster without compromising any of our results. And this has been something that's been really, really nice for the project we're doing in Durham right now with the city parks, because we're collecting 200-300 samples per park, and it's something that we're really trying to move through quickly. So this has really helped in that respect.
Thank you, Julia. So the next slide are a couple of examples of 1950s articles that are our major way of learning about the neighborhood city-run waste incineration. And so they're both from 1950s. The picture on the left, it's a little bit hard to see, but that's a bulldozer up there kind of cleaning up the cinder and ash pile that existed in what today is about a 10-acre city park in a residential area. And so the details say here, this is Walltown Park, which is our first park we've sampled and analyzed. the paragraph there tells us that there were 200 or maybe 2,000 truckloads of cinders and ash removed from the park, and then the remaining cinders and ash were smoothed across the park, and then a topsoil layer was added as well, and then benches were installed, and the city was pretty happy with its, you know, in an innocent sort of way, they were moving ahead through the 20th century. So we're very conscious of we're taking care that we don't alarm the city. On the other hand, city parks need upgrade, and you know that's where we're going. And let me just share you the excitement of science in process. So these are unofficial data. Here's Walltown Park. Here are the locations of each of the surface soil that we took across the park. And here's a new gym facility that's been constructed in the last 30 years. This square that's blackened is what we initially thought was the location of the park, of the incinerator. It might have been a little bit to the north, but it's pretty close. So that was the old incinerator site. And these are concentrations of lead on across the park. We've taken these data, and Annie has put them into her GIS program and krieged the results, which means interpolated them. And you can see there's a hot spot that's surrounding around the incinerator. And when we interrogate the old aerial photos from the 1940s and 50s, we hypothesize that a lot of the ash and cinders was actually transported to the other side of this creek and moved down to the southern western end of the park. And sure enough, our data kind of are suggestive of that. The intensive horticulture around this building reveals quite low concentrations, which is good. There are some scattered high points there. In any event, this hot spot over here is a problem area. It's the location of two horseshoe pits that are very popular here. And so we've got some concentrations there that are up there in 270 to 450, you know, right around the horseshoe pit. So there again, I think we're moving to a recommendation that this is one park that needs, some facelift, if I can use that word. So we're in process here, and I'll just add, and Julia can feel free to add anything else. What's the future of our work with this XRF? Definitely want to continue our soil studies in Durham. There are 4 of these parks that are incinerator that were originally incinerators. We'll complement those studies with some parks that are not incinerator, don't have incinerators in their history. I have a monthly Duke Soil Lead Talks blog. It's a blog of sorts every month. The next one is by Dr. Brett Erickson. We've had these going for a number of months. It's on 2nd of February at noon Eastern Time. If you want to join in, email me, please. Yeah, he's done amazing work. We want to, as I mentioned before, we have ambitions to resample soils in 6 or 8 American cities in different climates with different soil chemistries. Cities that have had their soil sampled in the past, so we can investigate the decreases that are occurring in soil lead, the hypothetical decreases. And we always want to work in a way that helps educate the next generation of scientists, just like Julia. Amazing. So if you want to follow up, here's a Google and an email. Julia, got any last words?
I guess I would just say, we're a soils lab, so we're moving forward with the soil in Durham using our XRF. But I've seen XRF in literature used with metals, with sands, with different kinds of like food materials. I've done work with different kinds of coal or water. So this is really just, I think, an adaptable instrument, which really kind of makes the possibilities not only like in our lab, you know, intensive, but just some serious opportunity for almost every field of research with XRF, which makes it super exciting, I think.
Yeah, so how do you want to move forward, Michael?
Yes, thank you. That was a very stimulating presentation, and we've got lots of good comments coming in here. I was you may have saw my head down periodically. I was writing lots of questions. I could dominate the whole Q&A time with my own questions, but we've got really good engagement here from our attendees. I wanted to pose a two-part question to you that has come in from several people here. The first part is, should everyone just panic and sort of crawl under the table here, or could you give some maybe guidance around what would be some indicators that they should be concerned about their own soil and then go to the next step of testing? So what are some indicators for concern? And then if they do see it, what are mitigation strategies that are available to them? We have a lot of people on today, I think, who are interested in sort of community farming and urban gardening. So if you could speak to those 2 points would be great.
Yeah, when I think about gardening in the city is a really amazing occupation and a wonderful activity. So each of the contaminant metals has different potentials for being taken up by plants. Fortunately, lead is a chemical element that plants do not take up very readily. Some of the other metals do, but lead is not one that you typically have to worry about the roots taking up the lead and translocating them up to the fruits. Now, if you're growing a root crop, potatoes, that's another matter. Or if you're growing leafy greens, the splashing of soil particles that might occur onto the foliage is of concern. But the internal biomass of leafy greens or above ground fruits and vegetables is not likely to have much lead. That doesn't go for all of the metals, but a recent review paper was just published. It's a very good one, very thorough, that is very comprehensive in coverage of the literature and really establishes that point, that lead is just not taken up by plants very, very readily at all. There are a few species of plants that do take lead up. They're very, they're unique and on their own. So I was happy to see this review paper come out. It was just published that more firmly established that rule of thumb that I've just given, because there is a general way of thinking and a general concern about soils in the city being rooted by plants taking up lead into the plant biomass. I think that New York City gives me, at least, speaking for myself, the best roadmap for remediation in cities. And basically, it's very, very costly. Soil is very heavy. It's hard to move soil around in terms of excavating it and moving it off-site. What I think cities that have parks like the one we're looking at, maybe there'll be some excavation here or there, but basically it's more a matter of coverage. It's more a matter of bringing in soil that is geologically, has the geological level of lead, which is 10 or 20 parts per million, and basically covering the surface environment and then stabilizing that environment, either with mulch on top or with mulch and plants, even better yet. Yeah, there's quite a bit of interest and quite a bit of help that you could get if you either email me or look online for what New York City is doing. It's one of the best things that New York is doing, frankly. It's really quite incredible, their programs, which have been going for about 10 to 15 years.
Thank you. And I would point all our attendees to the attendee chat section. If you haven't already found it, there should be a sort of a caption icon in the lower center of your screen. And there's actually a very vibrant conversation that's going on right now in our attendee chat section. We have with us George Lozevsky from the New York City Urban Soils Institute, and he's sharing some of his some of his work from NYC. Can you comment, Professor Richter, on any other metals besides lead? Have you looked at those at all? Or your research hasn't looked at maybe other RCRA metals or toxic metals, cadmium, mercury, arsenic, or anything like that?
Yeah, and I think that this is a question I could maybe encourage some interaction with Julia or somebody like Julia. We bought our instrument specifically to get into the field of legacy lead contamination, knowing full well that there's a whole family of metals out there that we brought into our cities that are generally insoluble, many of them, and that present problems across the city. But we bought our XRF specifically for lead, and we've been slowly looking at our other metals that are measured each and every time we push the button. 20 seconds later, we get total lead. We also get a total estimates of something like 20 other metals at least of interest, of potential interest. We've slowly expanded our confidence in those metals. I've decided to go kind of slow on this for several reasons, but we do know that, for example, arsenic is as impressive in terms of the correlation and the quality control as lead is. Lead we can put on a linear line, like we showed before, over 5 orders of magnitude. I don't know if arsenic spans over 5 orders of magnitude, but it may, and it's strongly linear. Several other metals are linear as well. I've taken a cautionary approach, but there's definitely an opportunity for somebody like a Julia to work with us and work across the elements and make our instrument much more of a have much broader interest. Our data sets are, like I was saying before, automatically accumulating concentrations of on the order of 20 other elements.
That's great. That actually, oh, sorry, please go ahead, Julia.
Dr. Richter mentioned running a long-term science experiment in South Carolina. It's basically a pine forest at this point. And we have been looking kind of at that data set to look at elements over time. And I think we saw some really interesting correlations between different elements and different kind of depths in the profile with maybe cadmium, magnesium, chromium. So there's definitely an opportunity in Durham, because the historic source is predominantly lead. We've really only been looking there, but certainly in other fields and other work, we've been aware at least of other heavy metals and their correlations.
Good.
Thanks, Julia.
Yeah, your comments there, Professor Richter, flowed into another question that was posed, and I think you partially answered. I want to make sure I understood your response well. But the question was posed about the accuracy and precision of portable XRF for metals other than lead. And if I understood you correctly, I'll ask you to confirm or correct. But you're saying when you've expanded your lens to look at other metals besides just lead, you're still seeing very good precision in the performance of the XRF. Is that accurate?
Yes, there's a small handful of them that we know are responding linearly. I've bought a lot of scientific instrumentation over my time as a scientist, one thing I like about this instrument is the technical support. You'd think we're being paid, Julia. This is so funny, but I can honestly say that we've had several people on the call, Michael, yourself included, and you've helped us initiate our studies. but then I also anticipate as we get serious about the other elements, which I want to get I want our lab to achieve that ability by the time we resample cities across America. I want to collect that's a much more interesting project. If we're going to go to the hassle of having our colleagues in New York recollect samples, Baltimore, Indianapolis, Los Angeles, Phoenix, who'd I leave out? If we're going to collect that kind of sample, we want an XRF that'll give us 20 elements. And so we'll have a much richer data set, and I can foresee some good consultation with you guys, as well as my colleagues in other soil chemistry labs.
Yeah. Thank you for that. We're certainly at Olympus committed to giving customer support. It's something we sort of pride ourselves on, and we'll be happy to support you and other clients as well.
I don't see the questions, Michael. So we're depending on you.
Yeah, no worries. I'm trying to post them, voice them to you as we go along. We did have a question here about bioaccessibility related to plants. I think you touched on that in part. That you were, if I understood you correct, very little of the lead is uptake into the plant itself.
Yeah, so that's a major area of research, especially among my colleagues. I paid attention to total lead for several reasons, but I do know that, for example, there's a whole cadre of EPA scientists here in the Research Triangle. There are scientists elsewhere who are trying to take soils and estimate, how much of that total lead is bioavailable. That's very important. It's also, from my point of view, a very complicated question. And so I'm quite comfortable here at the present time and in the short-term future with total lead. I'll let others deal with those complexities of bioavailability. But one of the things that, a repeated sample in cities like has already happened in New Orleans, one of the opportunities that gives you is to look at the changing bioavailability over time. If you have a soil archive, or the changing lead chemistry over time, which must be occurring, but is absolutely a frontier in terms of a scientific question. Yeah. Good question.
Maybe I just pose to you, Julia, can you speak a little bit to just how you got so interested in portable XRF?
Yeah, absolutely. So I'm originally from Jacksonville, Florida, and I got really involved in science fair in high school and was super passionate about the coastal environment, and particularly coastal pollutants. So I started research in my sophomore year looking at remediation techniques for oil spills. And XRF was used a lot in, I want to say, the 2008 Deep Horizons oil spill, particularly with a professor out of Texas Tech at the time, or maybe LSU, but Dr. David C. Weindorf. And he was looking at using visible infrared spectroscopy, or near-infrared spectroscopy, and PXRF to determine oil content of different sands. So I reached out to him, and we got talking and kind of finishing up my work on coastal remediation techniques and coastal oil contamination. And then we partnered with a professor from Dickinson State University in North Dakota to start working on a really novel approach to quantifying the sulfur content of lignite coal, which is when we really got involved with PXRF. And that's kind of how I came to meet some people and Michael from the Olympus Corporation at a conference in Austin, Texas. And we basically saw that with a little bit of algorithm training, we could use the PXRF in lignite coal to determine sulfur content, which has some serious implications for sulfuric acid. But in doing so, we started kind of trying to adapt PXRF to maybe different mediums that it wasn't necessarily made for. And then my senior year, we again adapted it to a different medium and started working with water and heavy metals. And that really kind of brought me back to the PXRF and heavy metals. And then when I started at Duke, actually, Michael, I reached out to you and found the Richter Lab and haven't really looked back since. So now we're still doing great work with the PXRF and heavy metals.
All while playing basketball. Julia's a basketball star.
Wow.
She would never tell you that either. Julia, never lose your humility. It is so wonderful. Yeah.
Yeah, that's great. I'll just again draw attention to the attendees. Mr. Lozevsky from the New York City Urban Soils Institute put a nice reference about bioavailability into the comments. I've grabbed that reference. I will send out some resources to follow up, including this reference that on bioavailability that he shared. And I'll try to get from you, Professor Richter, that review article that you mentioned earlier. And for all the attendees here, then we'll follow up with some resources. I've already posted into the chat a link to your open access article from your Durham study, and I'll include that in the resources that we send out to all the registrants afterwards. Again, my name is Michael Hull, and if you have any questions about the work today, well, you should direct those to Professor Richter, but if you have questions about the technology, rental opportunities, soil analysis with portable XRF, feel free to reach out to me. I'll put my email address in the attendee chat, and you can find me on the Olympus website, or you've obviously found me when you registered for the email. So I think I'll give the last word to our presenters, Professor Richter and Ms. Gaglieri. Anything you want to say to our attendees?
No, it's so great that there were New York City folks embedded in a list I didn't see. I certainly didn't see. Certainly glad I didn't talk bad about the Big Apple. No, Zoom gives us a lot of ability to do these kind of things, Michael, and I'm glad you're making use of it. This remote technology, it's not for everything, but for occasions like this, it's really opening up another way to communicate and circulate. Yeah. So all I have to say is thanks for the opportunity.
Our pleasure.
Yeah. I would say thank you for answering panicked emails and phone calls about any XRF questions that we had, and to everyone who attended, thank you for coming and listening to us. And it's nice to know that we do great work, but when other people are interested in it too, it's a good feeling. So thank you.
Absolutely, absolutely. So thank you everyone for joining today, and we'll send the replay link out here shortly. Thank you, folks.